So let me just summarize where we are. We had some basic definitions, really almost no results, on homology, chain complexes and boundaries and cycles and homology. And then I gave a lecture on unbounded operators on Hilbert space. And essentially all the operators we're interested are closed and densely defined. And that also means that T star is a nice operator which is closed and densely defined. And the best thing about T and T star is the close relations between the null spaces of the null space of one is the orthogonal complement of the range of the other, and vice versa. Actually, so that's not true. This would be the closure of the range here. But then we often have closed range operators. And if the operator has a closed range, then of course I don't need the closure here. And T star have closed range together. So in practice, the operators we're going to come across are going to be closed, densely defined operators with closed range. So you don't have to worry about putting that bar there, and the same thing applies to T star. Okay, now we're going to put these together. We're going to make a complex of spaces in which are where the vector spaces are Hilbert spaces with, and the D operators are closed, densely defined operators with closed range. That's what we're going to call a closed Hilbert complex. The examples to bear in mind, we could, in R3, for example, or Rn, we have gradient from H1, which is a subset of L2, to L2 vector spaces. And if that's T, then T star is minus the divergence, and that's from H0 div, which is a subset of L2, to L2. And then we also have div from H div, and its adjoint is minus grad, but not minus grad with H1, that would be H0 div, but minus grad with H01. And we also have curl. And the adjoint of curl is curl, but if we take the domain to be H curl, then the domain of the adjoint is H0 curl. So the adjoint of grad div curl is div grad curl, and if we don't have any boundary conditions in the domain of the original operator, then we have boundary conditions in the domain of the adjoint operator, and vice versa. And just to remind you, H01, of course, means the functions satisfy u equals 0 on the boundary, but H0 div just means that the normal component satisfies 0 on the boundary, and H0 curl means the tangential components satisfy 0 on the boundary. Okay? So what's a Hilbert complex precisely? It's very simple and natural at this point. We have a sequence of Hilbert spaces. These are the base spaces W. These spaces are the spaces on which our unbounded operators are going to be defined, W0, W1, W2, etc. And on each of them we have an unbounded operator from WK to WK plus 1. And so it has some domain in WK. And then if you do two Ds in a row, you get 0. So that means that D of anything in its domain, that's the range of D, is in the domain of the next D, and the next D takes it to 0. So it's in the null space of next D. Okay, so we have these Hilbert spaces, W0, W1, and so forth. and they're actually infinite sequence, but they're 0 beyond a certain point. And then we have these domains, and since I'm doing a co-chain complex, those are the ones that come up the most, so they're superscripts. So the domain V0 and the domain V1 and the domain Vn, and then we have an operator defined on its domain, D0 and D1, etc. So that's our Hilbert complex. Now everything we know about unbounded operators apply. So Vk is itself a Hilbert space if you give it the graph norm, which means that the norm of something in Vk is the W norm plus the W norm of D of it. And this space is complete because we are assuming that the D is closed. Oh, so let's see. Yeah, it's a closed operator, so the domain with the graph norm is a Hilbert space. That's one of the equivalent definitions of closed operators. The domain spaces themselves, well, you could think of this as a Hilbert complex with bounded operators, with the W being taken to be the same as the V, and the norms being the graph norms. So the top complex it also fits under the definition of a Hilbert complex, and we call this the domain complex. Of the original Hilbert complex. So the domain complex is what you get if you throw away the W's. You forget about the W's, where the D's were originally thought to be unbounded operators, and just think of them as bounded operators on the domain. There's less information in the domain complex. You've forgotten the W and the W inner product. If you only had the domain complex, you couldn't reconstruct the W. That information is not here. So there's more information in that Hilbert complex of unbounded operators. Okay? Any questions? Okay, now the domain complex is also, if you forget about the topology altogether, it's vector spaces and linear maps, so it's a complex like we studied in chapter 1 on homology. It's a co-chain complex. So it has co-chains, which are just the elements of the domain, but more importantly, it has cycles, which are the null things in the null space, and boundaries. Really, I should say co-cycles and co-boundaries, but I won't be bothering with the co too often. And most important, it has homology, cohomology, which is Zk mod Bk, the vector spatial quotient. Now, we want to use the Hilbert space structure. This is a bad operation, taking Zk is a closed subspace of Vk, of Wk. The null space of a closed operator is closed. But Bk might not be closed. It depends whether the range of D is closed or not. Now, if you do this operation, if you mod out by a not closed subspace, you don't get a nice Hilbert space structure and topology and so forth. You get algebraic thing. So this is much more interesting if we assume that the range of B is closed, and then we just have a closed subspace in Hilbert space we mod out by. Okay, so that definition is Hilbert complex is called closed if the ranges are closed. Don't get confused with their terminology. We always assume the operators are closed. But their ranges may or may not be closed, and we call it a closed Hilbert complex if the ranges are closed. And as I said, if the ranges are closed, everything's nice, because in that case, we don't have to put this bar here, and we have this not perfect duality and things. And in fact, almost all the Hilbert complexes we deal with will be closed Hilbert complexes. We'll have closed ranges, and therefore these are both closed. And therefore, this is just taking a closed subspace and Hilbert space modding out by it. It's all very nice. One more definition before I go on is a Hilbert space is Fredholm if this space is finite dimensional. Usually Z and B are not finite dimensional, but the quotient is. That means the range has finite dimensional codimension, and there's a little lemma that says when that happens, the range is closed. So if this is finite dimensional, it's definitely closed. That's called a Fredholm complex, and so Fredholm complexes are closed. And in fact, all the complexes we'll deal with are going to be Fredholm. But if you'd like an example of one that isn't, and we won't deal with, remember in our de Rham sort of business, one of the homology groups is a number of holes. Well, suppose I put in infinitely many holes. Then we would have problems. That's a domain without a Lipschitz boundary, a horrible domain. We're not dealing with that. Okay, so one of the main things we do with closed densely defined operators is take their adjoint. And so if D goes from WK minus 1 to WK, D star goes from WK back to WK minus 1, and it has its own domain, V star K, and it's also a closed densely defined operator. Now, so then we have this sequence of spaces with the D stars now going, it's now a chain complex with the indices going down. With a typo here, damn. That should say V star, superstar n minus 1, and V superstar n. So we have the dual complex, the dual of V super n, the dual of V super n minus 1 with the D stars. And I claim this is also a complex. In other words, I claim that the range of D star is contained in the null space of the next D star. And how does that go? Well, the range of D star, even if it's not a closed Hilbert complex, it's contained in the range of D star closure, which is equal to the null space of D, orthogonal complement. Now, the null space of D contains the range of the previous D, because the original complex is a complex. And so when you take the orthogonal complements, you reverse the inclusion. So this is contained in the range of D orthogonal complement, and the orthogonal complement of the range of D is the null space of D star. So the range of D star is contained in the null space of D star. So whenever you have a complex, you have a dual complex. With different operators in different domains. And as I said, we're mostly interested in complexes where are closed, all the ranges are closed, and we know that means that the dual complex also has closed ranges. And so from now on in the course, we're mainly going to be dealing with closed Hilbert complexes. Okay, and now here's the main thing that we get by bringing a Hilbert space structure to homology. This is really the difference between de Rham cohomology theory and Hodge theory. And that's, you don't very often work with quotient groups inside a Hilbert space. You usually just take the orthogonal complement, right? Whenever you have a Hilbert space X and a closed subspace Y, you have a canonical isomorphism between this with the closure, with the orthogonal complement of Y inside X. So the space X breaks up, of course, as Y orthogonal. I'm going to use this symbol, an ortho plus a Y plus Y complement. And this is isomorphic to X mod Y. So we're going to apply that over here, and we're going to define a space which is called script fractor Greek German HK. HK is going to be defined to be the orthogonal complement of the closed subspace B inside the null space. Okay, or another way to write it is you take the orthogonal complement of B and intersect it with the null space Z. Okay? So that's the usual story of orthogonal complements in a Hilbert space. Let's say the whiteboard is Z, all the cycles. Of course, it's probably an infinite, it might well be an infinite dimensional space. And inside it, it has all the boundaries, which might be another infinite dimensional subspace, which we assume to be closed. Then the homology group is, by definition, you take points in Z, and you look at their equivalence class, modulo B. What does it mean for two different points in Z to be in the same equivalence class? Well, it means their difference is an element of B. So the equivalence class is this plane parallel to B. Okay? And so without using the Hilbert space structure, the homology is just the collection of all these planes regarded as individual objects. That's homology class. But when we're in a Hilbert space, we can take the orthogonal complement of B, and that will intersect every homology class in a unique point. So we call this orthogonal complement of B inside Z, that's H. It's called the harmonic forms, for reasons that'll become clear. These lines, despite appearances, are parallel to each other, by the way. And so in every homology class, there's exactly one harmonic form. In fact, it's the element of the homology class of lowest norm. And so the homology space is isomorphic. The cohomology space is isomorphic to the space of harmonic forms in this very natural way. And so instead of dealing with equivalence classes of cycles, we can just deal with these particular cycles, the harmonic forms. So now we can make use of one more thing. We can make use of the adjoint to define this, because the orthogonal complement of the range of D is the null space of D star. The null space of D star is Z star by definition. So these things are equal to each other. And that means the harmonic forms are Z star intersect Z, or Z intersect Z star. So it's another way to show harmonic forms are very simple. They're things that are in the null space of D and in D star both. And those things are exactly a set of representatives for the cohomology. Okay, so there's not too much more to say about it because it's all very simple, but it's very, very fundamental. So I don't want to rush over this point. So the harmonic forms HK are defined to be ZK intersect ZK star. So they're everything in the domains of both the operators, and so both du and d star u are equal to 0. And we have that they give you the cohomology. They're isomorphic to the cohomology. Okay, I don't know if you noticed yesterday my clever color coding scheme. When the slide background turns to orange, it's a concrete example, typically R3 or Rn. So typically it's some variation of this same example that we keep coming to. So let's look at the Durham complex on R3 as an example of a Hilbert complex. So the complexes are going down now instead of across because it fit better on the page. So the W spaces are all L2, either L2 scalar fields for the 0 forms and the 3 forms, or L2 vector fields for the 1 forms and the 2 forms. The operators are grad, curl, and div, and all the other ones are 0. The domains are everywhere where these operators are in L2. They're the set of things in L2 such that the gradient is going to get us back in L2. So that's H1, H curl, H div, and then all of L2 for the last one. The adjoints are what we figured out last time. The adjoint of grad is minus div. It's written down here because it goes back from the next space. And its domain is H0 div. The adjoint of curl is curl, and its domain is H0 curl. And the adjoint of div is minus grad, and its domain is H01. Then the harmonic forms then are isomorphic to the cohomology, so we know these are finite dimensional spaces sitting inside the intersection. Well, the first ones are sitting inside H1, the intersection of H1 and L2. The next one are in H curl and H0 div and so forth. And their dimensions are the Betti numbers, so the number of connected components of the domain, the number of tunnels through the domain, the number of voids inside the domain, and 0 for the last one. And these are the domain complexes, H1, H curl, H div L2, and the domain complex for the adjoint sequence, which is the same thing only with zeros over the space. In a sense, I should put a 0 over L2, but there the point is that an L2 function, the trace is nothing at all. The trace is 0, so there's no condition. And I'll just say I could have made a different choice. I could have started out with this complex and said that's my primary complex. The minuses don't matter, with or without the minuses. I could say this is my primary complex with the boundary conditions. And then I could say the adjoint complex would be this one here. So you can do it either way. So
you said the original Hilbert complex would contain more information like domain complex.
right, because, so you can see this here. Well, so let's take an example. Let's look at we're going to get to the abstract Hodge-Laplacian in a minute, but let me do this just in advance to sort of get you thinking on those lines. So let's take the very end of it, the complex. So these two spaces. We're going to use this to define a kind of mixed Laplacian where we're going to look for U in here and sigma in here. And basically we're going to, so we have our D operator here, which is div. And so we're going to find a sigma in H div and a U in L2. And it's supposed to satisfy basically sigma is equal to minus grad U and div sigma is equal to F. Okay, the Laplacian, the mixed Laplacian. How are we going to write this down in a weak formulation? We're going to have the inner product of sigma and tau plus or minus the inner product of div tau and U is equal to 0 for all tau in H div. And div sigma V is equal to FV for all V in L2. Right? Many of us have spent a lot of time with that system solved by mixed methods. I claim that you can't get that just by looking at this sequence. So if I try to abstract what we're doing here and say, well, I have Hilbert space Vn minus 1 and a Hilbert space Vn and a map D and lead to this system. Because not all the ingredients I needed to write down this system are in this diagram. L2 is here. H div is here. The operator div is here. The L2 inner product of scalars is here. But there's nowhere here L2 vector fields. Doesn't show up in this system. H div is just some Hilbert space, and its inner product is the H div inner product. The L2 inner product isn't showing up here. So I wouldn't be able to write down this in an abstract setting. I need further information that there's a bigger Hilbert space, L2 omega R3, containing this with its own inner product, and that's the inner product I use down here. Okay, so the bigger picture that also includes this bigger norm and then says, well, div is only defined on a subspace of the bigger Hilbert space, that has all the information that I need. So that's what I mean by there's more information when you remember it's an unbounded operator defined on L2. If I just give you the space H div and I say, what's the base space of this that it's included in? Well, I mean, it doesn't make any sense in an abstract sense. A Hilbert space doesn't have a base space. I have to say what it is.
Well, you can get all the, what is it, just put this aside for a minute. Just think about the domain complex which you mentioned earlier. Can you get around without
And my answer is no, you don't have all the information in that. Most of the information is in that. So I give you, that's what I was trying to say here. I give you, here's the domain complex. HDiv, L2, 0. We don't need the rest of it for this problem. So imagine we have that's our domain complex. You cannot write down the weak formulation for the Laplacian.
Well, when you do the weak formulation for Laplacian, you have HDiv. When you do HDiv, there's an L2 there.
No, well, but now you're using the internal definition of H.
The HDiv is the graph norm of the div.
Exactly. HDiv is.
But you can think it's just the HDiv norm. I don't know.
No, but so I give you the HDiv norm. You can't extract the L2 norm from it if you don't know.
Well, in this particular example, if you do HDiv, there's L2 sitting there.
Because HDiv is known to be the graph norm of a certain operator on L2.
Yeah, I know.
That's what I'm saying. If I give you a Hilbert, so suppose I say, let's abstract this. Now I'm going to give you a Hilbert space X and a Hilbert space Y and an operator. What's the equivalent of L2? I mean, there's not some, so you have to say, I mean, it's not very deep. All I'm saying is in addition to giving the domain complex, you have to say, well, these are sitting inside a bigger Hilbert space.
Complex, but it's not a chain. Hilbert complex is not a chain. You don't have
The domain complex is the chain complex, but the W's themselves are not because there's no operator defined on them everywhere. Johnny? Yeah, I guess I can say something about this now. Was I waiting for anything? Let me wait for a slide and then I'll do it. So that's a very good question. We should know precisely what the harmonic forms are. Let's do the first row. First row we can certainly say. So the first row is the set of H0, is the set of U in H1, intersect V star k, but V star k is L2, so that actually throws no additional information on the first row, such that du, d is the gradient, and d star u, well, the first row is 0, so there's no further information. Right, so here I should have 0u is equal to 0. So this is if I just everywhere do it this way. HK is the set of U in VK intersect V star K such that dV equals 0, du equals 0, and d star u equals 0. That's the definition of HK. And now I've just filled in what these spaces are. And so for k equals 0, there's nothing here. And there's nothing useful here. So it's all H1 functions whose gradient is 0. What is that? This is constant on every connected component. If it's a connected domain, this is the constants. So if the domain looks like this, it's things that are C1 here and C2 here. The gradient is 0. Okay, and what's the dimension of this space? It's the number of connected components, which is what we said beta 0 is. Okay, now we're going to characterize this space in the next slide in a different way. It's the solution to the Neumann problem, Laplace u equals 0, du dn equals 0 on the boundary. Again, they're just the things that are constant on every component. That's the reason they're called harmonic forms, because they're the solutions of the Laplace equation. Now, the case of 0 is easier, because in the other cases, v star k and d star come into the definition seriously, and let's get that on the next slide. Okay, but if you've solved Neumann problems and you knew you always had to worry about modding out the constants, you've been dealing with harmonic forms already. Okay, so now I want to relate it to the Laplacian. Now, our context is, I'm not as orange anymore, I'm back into the blue abstract theory. So our context is that we have a closed Hilbert complex. And associated with that is an operator which, if I had done the de Rham complex, would be the Hodge-Laplacian. So I call it, for an abstract complex, the abstract Hodge-Laplacian. So here's our complex. Now, these are not everywhere defined operators. These are the W spaces, the L2-like spaces. And so these are only densely defined closed operators with closed ranges. And we have our adjoint complex D star going back. And if you start at one of these spaces, you take anything that's in the domain of D, anything that's in enough domains, then you can take D of it and get to WK plus 1. And if it lands in the domain of D star, you can take D star and come back. So anything that's in the domain of D and D of it's in the domain of D star, you can apply D star D and come back to the same space. And in the same way, if it's in the right domains, you can apply DD star and come back to the same place. And the Hodge-Laplacian is defined by adding those two operators, D star D plus DD star. And so it takes WK to WK, but it's not defined everywhere. It's only defined on things in the right domains. Okay, that's the definition of the abstract Hodge-Laplacian. What is the domain? Well, it's everything that's in the domain of D, that's VK, and it's in the domain of D star, and D of it's in the domain of the next D star, and D star of it's in the domain of the previous D. So that's the logical thing. If all those domains inclusions hold, then you can define the Laplacian of the function. And the first thing I want to point out, which is the analog of what we just said in the zero form case, is that the null space of the Laplacian is exactly the harmonic forms. So the word harmonic form is perfectly justified. It's just things whose Laplacian is 0. And now we're in the abstract setting where we just have this little bit of equipment of unbounded operators and chains. So all these things have very simple proofs that follow from the definitions. But I'll do most of them so we get used to it. What's that? The motivation is the de Rham complex, right? In the de Rham complex, we're going to get operators that combine curls and divs and grads, which are the main operators of mathematical physics. So we will certainly get the vector Laplacian, curl minus grad div. That's very closely related to, as we'll see, to Maxwell's equations, curl u equals 0, div u, curl u equals f, div u equals 0, and so forth. So many problems fit into this context. Okay, and surprisingly, even elasticity does, although not with this Hilbert complex, not with the de Rham complex, with a different complex. Okay, so it's a little bit like, you know, when you start out with finite elements and you say, well, consider the situation where we have a bounded bilinear form on a Hilbert space V and we want to find U and V such that BUV equals FV. What's the motivation? Well, the Laplacian, for example, is a problem of that form. And so we have problems of this form. Okay? So the first claim we have on this slide that needs proof is that the harmonic forms are just the null space of the Laplacian. So harmonic forms is the set of U that are in the domain of V and V star, and du equals 0 and d star u equals 0. And the Laplacian is dd star u plus d star du. So clearly, oh, okay, but not clearly actually, because I have to talk about the domain of the Laplacian. That's things in V intersect V star, such that du is in V star and d star u is in V. So the claim is that if something's in here, it's actually in the domain of the Laplacian, and its Laplacian is 0. Well, its Laplacian in 0 is obvious, because du is 0 and d star u is 0, so if it's in the domain, then we write this down, and those would both be 0. But how do we know that it's in here? How do we know that du is actually in V star? Well, du is 0. So it's certainly in V star, and d star u is 0. So this space is certainly contained in this space, and L of u is certainly 0. So that means that harmonic forms are contained in the null space of the Laplacian. How about the reverse inclusion? If you have something in the null space of the Laplacian, does it have to be that individually du and d star u are 0 and not just this combination of things? That seems a little surprising, but it's amazingly easily. Take Lu and take the inner product of that with u. Of course, this is 0. Take the inner product of 0 with u, and you get 0. So this is if u is in the null space of the Laplacian. Then we get that. Okay, by definition, u is in the domain of d star, and d star u is in the domain of d. That's part of the definition of u being in the null space of the Laplacian. So when I take d star u with u, I get the same thing as d star u, because I'm in the right domains. So this thing is equal to d star u plus du. So that's d star u squared plus du squared. And so the conclusion is that both d star u and du individually are equal to 0. So the null space of Laplacian is contained in the harmonic form. So they're equal. And then the one other thing, so it means that the Hodge-Laplace problem, so here's the Hodge-Laplace problem. Well, we'll start at it and then I'll modify it. Abstract Hodge-Laplace problem is to find u in the domain of the Laplacian is given f in wk, find u in the domain of lk such that lu is equal to f. That's the obvious problem. And that problem is definitely not well posed if the harmonic forms are non-zero, because it has a null space. Okay? So to make this well posed, I should put in the condition u orthogonal to the null space of L. Otherwise, there's no chance that it's a well-posed problem. Okay? For example, for the Neumann problem for the Laplacian, I shouldn't just write down this. This is never a well-posed problem. If it's a connected domain, I should also add this condition. It's orthogonal to the constants. But this is still not a well-posed problem, and that's still not a well-posed problem. And that's because if I take Lu, so suppose u is in the domain of the Laplacian, and I look at Lu, and I take its inner product with a harmonic form P. Well, then I do the same. So a harmonic form P is in the domain of L, L's in the domain of L, so we have all the domains we want, so we can move all the D's over as D stars, and this is the same as D star U, D star P, plus du, dp. It was d star up, and then I can move the d over to d star because everything's in the right domain. But p is harmonic, so d star p is 0 and dp is 0. So this is 0. So we've concluded that every harmonic form is orthogonal to everything in the range of L. Actually, this is our usual result about bounded operators, that the orthogonal complement of the range of L is the null space of L star, and L is self-adjoint. So the orthogonal complement of the range of L is the harmonic forms. So that means this is not a well-posed problem, because I can't give in this for any f in W. I can only, so if I have an f in W, well, f would split into two pieces. It would split into a harmonic part, the harmonic forms, some small subspace of W, and then everything that's orthogonal to the harmonic forms. The orthogonal complement, which is almost everything in W. So I should say W is splits in that way. So f is equal to the orthogonal projection of f into the harmonic forms plus the difference. And there's no way I can solve Laplace u equals this part, but I can solve Laplace u equals this part. That's orthogonal to it. So there's two ways I could write that. I could either write this equals f minus phf, or I could write equals f mod h. There's only one thing that you can subtract off that makes this solvable, right? So equivalently. So that's my abstract Hodge-Laplacian that has a chance of being well posed. If we came here to the case of the Neumann problem for the Laplacian, this would say, given f in L2, find u such that Laplace u is equal to f minus the average of f. It's a projection into constants. So that this is a function with average value 0, so I can solve the Laplacian with a Neumann boundary condition, and I make u unique by making it orthogonal to constants. Okay? If I have one component. If I have several components, there's a few conditions like that. Okay, and of course the Neumann problem for the Laplacian is well posed if you put in those conditions. And it's also true that this problem is well posed in this complete level of abstraction. So any problem that fits in this form is a well posed problem. So we want to show that. Okay, I'm going to give two other formulations of the abstract Hodge-Laplacian, sort of a weak formulation where we use test functions, and then a mixed weak formulation. So the primal weak formulation is going to be what happens if you take Lu equals f minus phf, and you multiply it by a test function v, and take the inner product. So obviously, we've done this already. If I take dd star uv, this I write as d star u d star v. And similarly, when I reverse the orders. So I'm going to get du dv plus d star u d star v should equal f minus phf v. That's what I would have. And so here, I'm again given f and L in W. I want to find u. And now here, in the weak form, it looks weaker because I need u to be in the domain of D for this to make sense, and u in the domain of D star. But I don't need du to be in the domain of D star or D star u to be in the domain of D. So I can look for u in V intersect V star. And then this makes sense, and here I would put V in V intersect V star, and that makes sense. So it's formally a weaker formulation. But I still have to take care of the fact that u is orthogonal to harmonic functions, so here I should intersect with the orthogonal complement of the harmonic functions. And I can do the same thing here. If V is harmonic, this side is definitely 0, and this side is definitely 0, so I don't need to use the harmonic test functions. And once I do that, if V is orthogonal to harmonics, this PHF is unnecessary, so I can get rid of it. Could leave it there or not, as I wish. Okay, maybe I should continue with this Neumann equation example. Instead of this strong form, now I'm doing the weak form, which would be to find u in H1, intersect L2, intersect the orthogonal complement of the constants. It should be orthogonal to constants, such that grad u, grad v equals, these are L2 inner products, equals the inner product of f with v, for all v in H1 orthogonal to constants. That's the weak form of the Neumann problem. V is the domain of... Yeah, because this is a simplified example, I'll do the other forms. This is the case of zero forms. So here was our complex, H1, H curl, H div, L2, 0 coming in, L2, 0. And in this case, I'm in this situation where I'm using D0, and I have D star 0, and those are, I should actually have a minus here. This is grad and div, so this is minus div grad, Laplacian. These operators are 0 in this case. That's why I only have 1. But in the other case, when I move over here, then I'll have operators both ways, and that's why I'll get curl, curl minus grad div. Yeah? That comes in the fact that du is in the domain of v star. So, yeah, this is good that we go through this example carefully. So our v is h1, well, v0 is h1, and then v star 0 is just L2, and then we go this way and we get V1, which is H curl, and V1 star, which is H0 div. And when I say find u and du dn, what I really mean is to say, so the domain of the Laplacian, the zero Laplacian in this case, is the things in H1 that are also in L2, and then d of u, that is that grad u, is in H0 div. And the d star of u is 0, so we don't need it. So what is this? Well, this says that div grad u is in L2. So this is a set of u in H1 such that Laplace u is in L2. But also grad u dot n equals 0 on the boundary. And that's du dn is equal to 0 on the boundary. So that's the domain of the Laplacian in this context. It's things in H1 whose Laplacian is in L2 and whose normal derivative is 0 on the boundary. There's something really nice about this theory. I could tell from some of Jin Chao's question, he's saying, well, isn't this really just the same as we usually do with H1 and H1 star and so forth? But you won't hear me talking much about elliptic regularity. You won't hear me saying, well, if omega is a smooth domain or a convex polygon, then u is in H2, so Laplacian makes sense. Because I'm not trying to show that this Laplacian makes sense because u is an H2 function, and therefore Laplacian u is in L2. Namely, I'm working in the space of functions whose Laplacian u is in L2. And I have the regularity that the solution is in this space by definition. If f is in L2, then the solution to Laplace u equals f is definitely in the space of things whose Laplacian is in L2. So elliptic regularity gets finessed away in this theory for many purposes. Any other questions? I appreciate the questions. Okay, so the primal weak formulation is to find u and v intersect v star with the side condition it's orthogonal to the harmonic forms, such that du dv equals d star u d star v, comma du dv is equal to fv for all v in v intersect v star. And as I say, it looks weaker. So what's obvious is one direction, that let's call this the strong formulation. And it's obvious that the strong form implies the weak form. If we have a solution of the strong form, it's a solution of the weak form, the primal weak form. The primal weak form is lousy for numerics in many applications. It's fine for that problem over there. We know you can solve the Neumann problem for the Laplacian. But remember the examples I gave yesterday of the L-shaped domain and the annulus. Those were examples where I solved this problem, where this was div and curl. And I used the primal weak formulation and standard finite elements, and it didn't work. The reason is because this space is difficult to find finite element subspaces of for two different reasons. First of all, if there's harmonic forms, this side condition is not easy to impose at the discrete level. And second of all, even if there aren't harmonic forms, if the domain does not have nice smoothness, V intersect V star is not such a nice space. It's not a standard Sobolev space. But here in the abstract business, and for considering not the numerics, but just the well-posedness of the problem, it's a perfectly nice formulation of the problem. And now finally I want the mixed weak formulation, or the dual weak formulation, well, the mixed weak formulation. So again, we start with an F and W, and now we want to find I'm going to introduce two new variables in this formulation. I'm going to introduce sigma is d star u. So that would be in, well, if I start with a solution of the strong form, then this would be, by definition, d star u is in V, Vk minus 1. And I'll also give a name to pH of F, the thing you have to subtract off from F to get something in a well-posed problem.
Can you just assume F is going to be orthogonal to H in the beginning?
Yeah, you could do that.
You need a consistent data.
You want to take my notes and go through and change everything? You could do it either way. It's probably, I think this is probably the way to do it, but you could do it either way. So now what we want to do is we want to find sigma and u and p, and they should be in Vk minus 1 and Vk and H. I can write for another 2 lines, or is it too painful in the back? Anil, is this okay if I write down here? Okay, let's not do it. So, by the way, I'm just writing what's on the slides, so maybe that wouldn't be a problem. Yeah, so the back row can read the slides. So then I want the inner product of sigma and tau. Of course, this is the inner product is always the W inner product unless I put a V in it. So this is the WK minus 1 inner product. And then I have minus d tau u. This is the WK inner product. And this should equal 0 for all tau in Vk minus 1. All tau in the domain of D. So the spaces are certainly natural because tau is in the domain of D. So I can put a d tau here. Let me write the other two equations, then I'll go back and say what this stands for. Okay, then the next equation is d sigma v. That would be in the W inner product, the WK inner product, plus du dv equals fv for all v in Vk minus 1. Okay, so that's the second to last line on the slide. And everything makes sense here because sigma by definition was in the domain of D, and U was in the domain of D, and V is in the domain of D. All I use is D's. There's no D stars in this formulation. And then I have to have the condition that U is orthogonal to the harmonic form, so UQ equals 0 for all Q in H, which is the last line on that slide. So let's look at this and see that this makes sense. Well, it makes sense, certainly. All the inner products make sense. All the D's make sense, and they're just L2 and W inner products. The first line is nothing other than the definition of sigma being d star u. So the first line, all I've written down is what it means for sigma is equal to d star u. So the first line is that. The second line says that d sigma, and now this term, if as long as du is in the domain of d star, this would be d star du. So the second line says d star d sigma plus d star du is equal to f, and that actually shows I made a mistake because that's not possible. It should be f minus phf. So I have to add one more term here, which is PV. So here I should have written du dv plus PV. And then it says d sigma plus d star du is f minus P. And since sigma is d star u, this is really d star u plus d star du is equal to f minus P. And so we're finding a harmonic form, P, such that the Laplacian of u is f minus P. So P has to be pH of f. It's the only possible solution. Okay, so what have I done so far? With the weak formulation, well, I said if all these sigmas and u's are in the right domains, like if we take u to solve the strong formulation, then they would all be in the right domains, it would solve the weak formulation. So again, it's pretty obvious that the strong form implies the mixed weak form. But now there's a result that may be a little bit surprising. And that is that this is an implication in both directions. Both of these are implications. So all three of these are totally equivalent under no additional assumptions. Okay? A solution of this solves this and this. A solution of the primal solves these two. And a solution of the weak solves these two. So they're completely equivalent. Of course, when I say a solution of the weak solves these two, I mean the u solves these two. And when I say a solution of the say the primal solves this, I mean if you solve the primal u, and if you define, if u solves the strong form or the primal weak form, and P is PHF, and sigma is d star u, then sigma up solves the weak form, and that was the one that was obvious. And then vice versa, if sigma up satisfies the weak form, then u solves the strong form.
So this is because this strong area is weakly defined.
It's because it's defined through unbounded operators and domains and stuff. But I mean, it takes a proof, right? We have to show that this is true.
Can I have a question, please? Is that a reasonable assumption the dual of this domain Vk is continuously embedded? No, I'm sorry. This Vk is continuously embedded into its dual.
No. The Vk is Hdiv, and Vk in our example is H1, and the dual.
I'm talking about the dual in the sense of continuous functional. Is that kind of dual?
Now you're moving into a different context, and what you're saying is, let's identify W with its own dual space, and then we have the mapping from W star into the other kind of dual of V star, and that gives us a mapping from this into this.
So
that's true. You could do that.
Your way of getting around this is by introducing Hilbert complex. If you assume that V is contained in V star, then you can get so in that formulation you can do F to be in the dual of V, which is a larger class, I suppose.
Yeah, but you have some problems here. So let's say we did your approach. So you're going back to the French approach, let V be contained in H, which is identified with H prime, which is contained in H is now called W. I mean, it's a beautiful theory. So you have Lyon's triple or whatever. So if we did that, then this F would be, for that problem, in H minus 1.
Yeah, that's
And,
a larger class.
And this problem wouldn't make any sense because the mixed problem doesn't make sense with it in h minus 1.
Would that be the dual, just the other dual?
Well, think about the mixed Poisson equation. The bottom equation is the integral of div uv is equal to integral of fv for all v in L2. So f has to be in L2 for that.
Oh, yeah, right. Okay.
So the Lyon's triple is not perfectly matched up with mixed finite elements. So the purpose of this approach is to make the definition so everything's as clean, as elegant as possible. Obviously, you can do it in other ways.
So in the strong form, can I say that so I could have, wait a minute, but in the weak form, f can be in the dual of v in the other dual. Because,
In this form,
yeah.
this v for the mixed Laplacian is L2.
Oh, that's L2.
So f has to be L2. Okay, so I have these three formulations. They're all very neat and clean in this notation and language, and I claim they're all completely equivalent. So that's the first statement of the theorem. And the second theorem is that they're all well posed. So under no further assumptions than I've made, there is always a unique solution to this and this and this, and they're the same. So that sort of shows that this is really, the hypotheses have been put together in the right way. So what has to be proven here? I think it's worth going through it, even though, it's subtle points, because formally they're equivalent. But what has to be proven to make them not formal? Let's see. I seem to have skipped something important. Yeah, I think when I was fiddling around, I missed a very important slide, but this is a perfect place for it. Actually, Rick told me I shouldn't introduce results till I need them, so people see what I need them for. So now I'm going to introduce a very important point, which are two key properties of all closed Hilbert complexes. And these properties will be exactly what we need to show that these problems are well posed and equivalent to each other. So we have a closed Hilbert complex, the WKs and the DKs with the domains VK. And the first is going to be the Hodge decomposition. So that's the first key property of whenever you have a closed Hilbert complex, you have a Hodge decomposition. So the Hodge decomposition is amazingly easy, and this is one of the reasons I love this theory. I remember the first time I heard about what they call Hodge decomposition, or has various other names, where everything can be written as a curl and a gradient and things like that. I was very confused about exactly when it's true, what am I assuming about the domain, and the boundary conditions. Here it's amazingly simple. So the Hodge decomposition is the following. We have the space W is equal to closed subspace Z. The null space of a Hilbert complex is a closed space, plus the orthogonal complement of Z. Okay, that's pretty obvious. Hilbert space is any closed subspace plus its orthogonal complement. But Z has a closed subspace B. Here's where I use the fact that it's a closed Hilbert complex, so the range of the previous one is B. That's a closed subspace, and so it can be written as that plus the orthogonal complement of B inside Z, and we gave that a name, which is H. Okay, so I simply substitute that into here. And so I get ZK plus, typically write it in the opposite order, HK plus BK. And we can, if we want, remember that the null space of D is the orthogonal complement of the range. Oh yeah, so it's not quite the order I usually write it in. I usually write the B first and the Z second. So it was the other one that I wrote in the wrong order. Or so I can also write the last space as B star K. So that's the Hodge decomposition. That WK, if you have a closed Hilbert complex, the W space is B plus H plus B star, orthogonal decomposition into closed subspaces. Couldn't be any easier than that, except something's wrong. Perp over here. Oh yeah, so actually I wrote everything in the right order, sorry. So Z plus Z perp, and Z breaks into B plus H, so it's B plus H plus Z perp. And if I want, I can write Z perp as B star. These are equal. That's the Hodge decomposition. Orthogonal decomposition into closed subspaces. And we could also ask about the V space, the domain of D. Well, Z is also, so I use the same reasoning. V is equal to Z, that's closed in the domain of D, obviously, also. It's the null space of the bounded linear operator D. So it's Z plus Z perp. And now what's Z perp? But now this is Z perp inside the domain, inside V, not Z perp inside W. So that's not the same space. Z perp inside V, this is the usual things that are orthogonal Z and W intersect V. Notice there's no difference between being orthogonal in the W norm and being orthogonal in the V norm, because the extra term has D's in it and D of Z is 0. Right, so to say that VW equals 0 for all W in Z, or to say VW plus DV DW equals 0 for all W in Z, these are the same because DW is equal to 0. But if I want to have the orthogonal complement in V, I have to take the things that are in V. Okay, and now what is this Z perp V? Well, the harmonic form, so Z perp breaks up as B and plus harmonic forms. And the harmonic forms are, when I intersect this with V, the harmonic forms are in V, so this part doesn't change, but here I have to intersect with V. So VK is equal to, I'll write it here, VK is equal to BK plus the harmonic forms plus, and here I can either write it as B star intersect V, or I could write it as the orthogonal complement of Z inside V, just like I could write this as the orthogonal complement of Z inside W. So there are two Hodge decompositions there. Well, I mean, if I have W and I want to know how to decompose it anyway. Okay, so that's one key property of all closed Hilbert complexes. And now let me state the other key property. So this is Hodge decomposition. And there'll be a slide on this when we put them on the web. And the other key theorem is the Poincare inequality. We need something quantitative. So when I say that these are well-posed problems, I mean also that the norm of the solution is bounded by the norm of the data, so I need something quantitative, and that's going to be Poincaré's inequality. And Poincaré's inequality is simply that if you take a V and you measure it, it doesn't matter whether you measure it in the V norm or the W norm, this is less than a constant times d of V. And now you look at that and say, so for example, in this case, this is the usual thing called Poincaré's inequality. The L2 norm of a function is bounded by the L2 norm of its gradient with some boundary conditions or something. But here it's a little more complicated because what if V is a cycle? What if dV equals 0? Then that doesn't imply V is 0. So we certainly need to input the condition that V is orthogonal to the cycles. And now the cycles, that's the space that some of it's in V, but some of it's not in V. If it's not in V, I can't even talk about dV, so I have to take the orthogonal complement in V, this space here. And so Poincaré's inequality is that there exists Cp greater than 0 such that this holds. That's taken care of by the statement that it's orthogonal to Z. The constants will be in Z, so that'll take care of it. In fact, in this example, so what I'll do in the last 5 minutes, instead of moving on and proving the equivalence in the weak formulation, I'll do that in the afternoon. I'll go to the concrete example here, and we'll look at that. So this will give us exactly that we remove the constants in that case. Okay, but before that, why don't I prove Poincaré's inequality, which is also trivial in this context. So actually, I mean, it doesn't quite rise to the occasion of a one-line proof. It's like a half of a line proof. You take D and you restrict it to the orthogonal complement of Z inside V. So it maps this Hilbert space to the next W. And it's 1-to-1 because I orthogonaled out I modded out the null space. And it has a closed range because we assume that D is a closed Hilbert complex. So this is 1-to-1 closed range. And we had a characterization for things that are 1-to-1 with closed range, which is a very easy characterization, which is that this inequality holds. dV is greater than gamma times V. That's exactly true of operators that are 1-to-1 with closed range. And how do you prove that? Bannach's theorem that says an operator that's onto has a bounded inverse, basically. So that's it. Yeah. What's that? What does it mean depend on V? There's not a universal constant. It depends on the particular Hilbert complex. So you're right. So for any closed Hilbert complex, there exists a Poincaré constant for that complex, which this is true. Actually, it would be 1 for every k, but there's only finitely many k's in our example. So. And by the way, it doesn't matter whether I take the V norm or the W norm here, because the difference is dV, and of course dV is bounded by dV. So. Okay, so let me finish with an example to hopefully make this concrete. I think I have a slide with that. Yeah, so let's do as much of what I've talked about today for the RAM complex in 3 dimensions. Okay, so on the top of this slide, we already had this. Those are the domain complexes. The W's are all L2. And now here's the abstract Hodge Laplacian. So that's d star d plus dd star. So for the zero forms, there is no dd star. That's 0, so it's just minus div grad, so it's minus Laplacian. So the abstract Hodge Laplacian for zero forms is minus Laplacian. It's a positive definite operator. And the boundary conditions that you get are that the function is, well, you get boundary conditions by forcing something to be in d star. The function has to be in d star, and d of it has to be in d star. So the function being in d star for zero forms doesn't tell us anything. But gradient has to be in H0 div. That's where we get the du dn. And I would call that a natural boundary condition because we get that boundary condition by the include. Oh, so I erased the abstract Hodge Laplacian. We get that boundary condition. If I go back to the here, we get that boundary condition from sort of having this term. This term here, we're going to have to be able to integrate that d onto as a d star into du, and so that's going to force a boundary condition, namely that du is in the domain of d star. So in that sense, that's a natural boundary condition. And what are the spaces we use in the mixed method? Well, for u, we use H1, and there is no sigma. Sigma is 0 in the mixed method, so there's only one space. So the mixed method and the primal method are actually the same thing for the zero form Laplacian. Maybe that's a good point to bring up. Except I'm going the wrong direction. So for the zero form Laplacian, there's no sigma and there's no tau. Those are the zero spaces. The only term that's left is du dv equals f minus pv. And the primal formulation, there's no d star u and d star v, so it's du dv equals fv. So for zero forms, there's nothing new in all this mixed formulation. It's just the usual thing. But that's only for zero forms. So now, what's the next operator? Well, then we start here. So we take an F and L2 vector field, and we curl it, and we add it to minus grad div of it, so we get curl minus grad div. What about boundary conditions? Well, the function has to be in the domain of minus div, that's H0 div, so that means we need u dot n is 0 on the boundary. And the curl has to be in the domain of H curl in the dual complex, the domain of curl in the dual complex, so that means the tangential components of the curl have to be 0. In the primal form, we required that u is in v star. That was built into the spaces, so I would call that an essential boundary condition. But the du ending up in v star was implied, not built into the formulation, so that's a natural boundary condition. So you could write this down in sort of very elementary terms like you would have before this course, and what we have is this. Well, let's do that. So we're trying to find u in H curl intersect H0 div. So this is the essential boundary condition, u dot n equals 0. And then such that the integral of curl u curl v plus div u div v equals fv. Let's not worry about harmonic forms for the, assume that we don't have any, for everything in H div intersect H curl. H0 div intersect H curl, same spaces. And when we try to integrate by parts, well, when we integrate this one by parts, nothing happens because V is an H0 div. We don't get any boundary term. But we integrate this one by parts, and we get that curl U cross N has to be 0 on the boundary as a natural boundary condition. So the primal weak formulation of the one forms here gives us this primal formulation of the magnetic boundary condition. That's what these are, magnetic boundary conditions for the vector Laplacian. And this was the formulation that I say is lousy for numerics, but it's perfectly well posed. What about the next one? So now we're trying to find, so this is k is equal to 1. Here's k equals 2. Then we're trying to find U and H div intersect H0 curl. Such that now the D operator is div. Div U, div V. And the D star operator is curl. And this would be for all V in H div intersect H0 curl. So it's the same problem, except that the 0 is on the H curl space instead of the H div space. So it's the same problem with different boundary conditions. And so we have the boundary condition U cross N equals 0 is essential. And the boundary condition from this one would be that div U equals 0 on the boundary. And that would be a natural boundary condition. And of course, you don't have to do it by writing out this way and integrating by parts. You just do it by looking at the domains up here. Same thing. And finally, what's the last one, the k equals 3 problem? Well, then we have some 0 operator, so things simplify a little bit. We're now looking for U in H01 intersect L2, which is just H01, such that the inner product of grad U and grad V equals the integral of FV for all V in H01. So now we're back to the first equation I wrote down on the first day of the course, the simplest boundary value problem, the Laplacian with Dirichlet boundary conditions. So the primal weak form for the n forms is just the Dirichlet problem. And the primal weak form, maybe I should have written down the k equals 0 case over here, just to keep the pattern going. Great to have all these boards. Remember, I'm ignoring harmonic forms. In all of these, if there are harmonic forms, I have to take the orthogonal complement. This is k is equal to 3. This problem, there are always harmonic forms, so I should be modding out by constants. This problem, only harmonic forms. So remember, here we have Betty 0, number of components. Here we have number of tunnels through the domain. Here we have number of voids. And the Dirichlet problem is always well posed. So we have these problems. Now what about the mixed form? So what about the mixed form? Well, in the mixed form, let me put that in red. Then we use two variables. Let's start with k is equal to 1, so nothing vanishes. Then we want to find a sigma in H1 and a u in H curl. And the first equation says that sigma represents minus grad u. that's not div, that's grad. So we have an auxiliary function, sigma, which is in H1, and we pin it down with that equation. And then we have curl sigma V plus, grad sigma V plus curl U curl V equals FV. So the mixed formulation for the k equals 1 problem uses the space H curl and auxiliary space H1 and uses the operator D, which is curl, and as auxiliary operator the previous D. Remember, the mixed form only uses D's, never uses a D star. They're only defined implicitly. So what is this? This is some mixed way to solve this equation, where we've introduced a new variable, sigma is minus div U. And then we get grad div U plus curl U equals F. Okay, what about over here? What's the mixed form? Well, then I would be looking, let's do it formally. My main space would be H div, where I'd look for U, and the auxiliary space would be H curl, where I'd look for sigma. So it's quite different than the previous one. The previous one, the auxiliary function was a scalar, sigma in H1. Now the auxiliary function is a vector, sigma in H curl. So I want to find sigma in H curl and U in H div. And then I have sigma tau minus curl tau U is equal to 0 for all tau in H curl. And curl sigma V plus div U div V is FV for all V in H div. So these are two different mixed formulations, both representing curl minus grad div, but with different boundary conditions. Let's look a little at the boundary conditions. What are the boundary conditions that we get? There are none built into the space. They're all natural. From this integration by parts, we get the u dot n is equal to 0. And by this integration by parts, we get curl u cross n is equal to 0. So, but now they're both natural in the mixed formulation. And here we get the two boundary conditions that we had for this problem, namely u cross n and div u is 0, but they come naturally from these two terms, this term and this term. So again, in all these cases, the boundary conditions are natural for the mixed formulation. Okay, now let's go back to the two n cases where things always simplify a little bit. What's the mixed formulation for three forms? Well, we're using two spaces, L2 and H div. And so we want to find a vector field sigma in H div, and the solution U is a scalar, which we seek in L2, such that sigma tau minus div tau U is 0 for all tau in H div, and div sigma V is equal to FV for all V in L2. So that's the usual mixed formulation of the scalar Laplacian with the Dirichlet boundary conditions. And if you've studied mixed methods at all, one of the first things you learn is that the Dirichlet conditions are natural in the mixed form. You don't put them in the spaces. They come out from integration by parts. In all our mixed forms, that's the case. And finally, let's go back to zero forms and write down the mixed formulation. Well, in that case, the mixed formulation uses only one space, H1, because the other space is 0, and this is the mixed formulation. So for zero forms, there's nothing new in the mixed formulation. It's just the primal formulation. Okay, and what about the Hodge decomposition and the Poincare inequality? And then I'll really stop. So let's start with the zero forms. What is the Hodge decomposition? Well, one of the terms drops out because there's no D star coming in there. So it's just that H1 is equal to, I'm sorry, there's no D coming in. There's a D star coming in from the other side. No, it's, what I mean is L2 is equal to the divergence of H0 div orthogonal complement with the constants. Let's assume that we have one connected component. Okay, that would be the first Hodge decomposition over here. W is L2. B is 0 because there's no -1 forms. H are the constants. And B star is minus div from H0 div. So, and this space, of course, is nothing other than L2 mod constants, sometimes called L2 orthogonal constants, sometimes called L2 hat. So this is the fact that any function in L2 can be written as the divergence of something in H0 div. Okay, what about the next Hodge decomposition? So then the space now is L2 vector fields. And that can be written as D's, which means gradients of H1 functions, plus the harmonic 1 forms, plus the range of D star, which is the curl of H0 curl functions. So an L2 vector field, if there, say first there's no harmonic forms, an L2 vector field can be written as a gradient of an H1 field plus the curl of an H curl field, and you can put boundary conditions on the curl field. Okay, that's probably the most common Hodge decomposition. What do they usually call it in fluid mechanics? Helmholtz decomposition, right. And that's not true on a domain that has a hole in it, a tunnel through it. Because then there are the harmonic forms that are orthogonal to both of these guys. And so you complete it by adding those harmonic guys. What about for two forms? Then we have L2 again. We have a different composition of L2 vector fields, which will just be Helmholtz with a different set of boundary conditions. It's now curl of H curl without boundary conditions, plus harmonic 2 forms. These are harmonic 1 forms. Plus grad of H01. So you have your choice when you do the Helmholtz decomposition of a vector field. You can write a curl of a function and grad of a function. You can put boundary conditions on the grad or boundary conditions on the curl, but not both at the same time. And that's violated depending on the topology for tunnels in that case and for voids in this case. And now 3 forms, what do we get? Well, that'll be relatively trivial again. So in that case, every L2 function is the divergence of an H div function without any boundary conditions. There are never any harmonic 3 forms in 3D, and so that's the whole thing. It's just a statement that div is onto. And finally, I owe you the Poincare inequality. Yeah. Oh, okay, that's a fair question. I did it for W, how about for V, is the question. So what does that mean? It means that we intersect the B star part with V. Um, so that would say H1 is equal to H1 intersect L2 hat, which is H1 hat plus R. This one would say H curl the gradient of H1 is already in H curl, so that part doesn't change. The harmonic forms are already in H curl, so that part doesn't change. But now we get curls that happen to also be in H curl. So it would be this intersect H curl. And then you could probably write this in various ways. So that means the thing is in H curl, and its curl is in L, and curl of it's in L2, and it has the usual boundary condition. So not much new coming out of this. And last, but far from least, is the Poincare inequality. So over here is what's often called the Poincare-Neumann inequality. It says that U in H1 is bounded by a constant times grad U in L2 for all U in H1 orthogonal to constants. That's the usual Poincare-Neumann inequality. We have to take inside V, which is H1, the orthogonal complement of the only null space of gradient is the constants. The next one would say that we have U in H curl, and its H curl norm is bounded by just the curl part, just the top part of the curl norm. But that requires that U in H curl is orthogonal to U is orthogonal. Well, so we can write it in two ways. That's probably the easiest ways to write it. U is orthogonal to the null space of curl. So U is orthogonal to the curl-free things. So U is in the orthogonal complement of curl-free things, which is also to say that U is in the range of which is the same thing as to say curl-free things are just the curl of H0 curl, the orthogonal complement of curl-free things. So if U is orthogonal to curls and it belongs to H curl, that's the same thing as it's orthogonal to the null space. Sorry. If U is a curl, see if U is in curl of H0 curl, then if I integrate this against something in the null space of curl, I integrate the curl by parts, I get 0. The boundary conditions here, so I can do that. So if U is such a function, or another way of saying that, if U is in the null space, the orthogonal complement of the null space of curl, and curl U is in L2, then U is bounded by curl U. Okay? So I don't know, which is the easier way to think about it? I think the easier way to think about it is in the null space. That's the way I wrote it over there. And so let's write down the other one the same way. It would say that the H div norm is controlled by the highest part of the H div norm. If U is an H div and U is orthogonal to the null space of the divergence. And the last case would be the usual Poincare inequality, which would be U in L2 let's see, no, what would it be, the last case? Would be U in L2 is bounded by 0 if U is in L2, wait, what is it? So in that case, V is L2, and Z is the null space of 0, so this is L2. Okay, so the last one doesn't say anything. It says U in L2 is equal to 0 if U is orthogonal to L2. So it doesn't say anything. There isn't. Everything is a cycle in the last space because the last operator is 0. The D coming out of is 0. So this is the 0 space. So it says 0 is bounded by 0 on the 0 space. So there's not. So I'm wrong. There's not a standard Poincare inequality. What is that? Where do you want boundary conditions? The boundary condition. So look at the form of the operator. No, it's right as it's written. Look at the form of the operator. The form of the operator is that U plus du in L2, that's our V norm, is less than a constant times just du in L2. So we don't really need this term because that one's obvious. For all U orthogonal to the null space of D. So that takes care, if it's orthogonal to null space of D, this piece can't vanish. Now this implies certain boundary conditions, being orthogonal to the null space of D. For example, being orthogonal to the null space of curl. And when I say the null space of curl, I mean any H curl function that's curl-free, the usual null space of curl without boundary conditions. Okay, to be orthogonal to all those guys, those guys, the orthogonal complement is the curl of things in H0 curl. And those are the boundary conditions that we need. And, so what would you like me? What are your?
It's possible to curl to 0. In the intersections.
It's not possible for curl U equal to 0 if curl is orthogonal to the null space of curl. Because if curl U equals 0, then curl's in the null space of curl. So it can't be orthogonal to the null space of curl.
U in the curl then, that only says that U is equal to the curl of some vector space, right?
Where? Sorry, here? Curl of a vector field with 0 boundary conditions, with 0 tangential components, and I also require U as an H curl. So it's that U is bounded by curl U for all U in H curl, such that curl U for all U in H curl such that UV equals 0 for all U curl V equals 0 for all V in H0 curl. That's the statement. This is the orthogonal complement of curl of H0 curl in H curl. So that's the statement. Now let's try to figure this out. This thing, if we formulate integrate by parts, we get curl UV plus the integral over the boundary of U cross N. That goes away, right? This goes away because we have V in H0 curl. No, I am confused. What am I doing wrong here? So let's start here. U is less than a constant times du for all u in the domain of D such that U is orthogonal to the null space of D. That's the statement which is trivially true because D is a one-to-one closed range operator from the orthogonal complement of the null space of D. So that's certainly true. So now we're going to take the case of one form. So this is H curl. And the null space of the curl operator with domain H curl, that's what it is. It's the set of V and L2 such that curl V equals 0. That's the easiest way to write it. So this is for all U and H2 such that UV equals 0 for all V in L2 with curl V equals 0. That's another way to write that. Okay, now, okay, now I know where I made my mistake. So now we need to, what's the best way for me to fix this up? Right. We need to use the Hodge decomposition. So I'm trying to characterize, but did I write it wrong here? I'm trying to characterize the orthogonal complement of the null space of Z. And maybe I screwed myself up because I wasn't being careful about my K's. Is that what I did? This is this. And what's this B star K? This is the range of D star. D star goes from VK. Okay. So V goes from VK plus 1 to WK. Okay. The range of D, those are, Rick, you can't help me out here? Where do we I have to get gradients into here? Okay, that's right. So V in L2, or in H curl, I don't know, such that curl V is 0. That's the null space of the curl from H curl to H div. If there's no harmonic forms, that would be exactly the gradients of H1. So this is also grad H1. That's what I need to bring in here. If there are harmonic forms, it's also, you have to add the harmonic 1 forms here. So this is the gradient of H1. And now we want the orthogonal complement of the gradient of H1. That's what I should have been writing down. So U orthogonal null space of D is the same. So the null space of D is the range of D star, of the previous D star, plus harmonic forms if they exist. Maybe here, let me write down something that I should have written down. I usually love this. I don't know why I didn't write it down. W, and actually I'll put the k's here. W is bk plus hk plus d star k. And this is the orthogonal complement of z. And this is z. That's how we got this whole thing. That's z. And while we're at it, this is z star, and this is the orthogonal complement of z star. Okay, and the Poincare inequality holds on the orthogonal complement of z. So it holds for everything orthogonal to this space, equivalently everything orthogonal, everything in this space, equivalently everything orthogonal to this space, z, which means it's orthogonal to gradients, the previous d. This is the range of the previous d, and also orthogonal to harmonic functions. So the usual way to interpret this one would be u is less than c curl u for all u in h curl, u orthogonal to gradients, and if there's any harmonic one forms, you would also have to be harmonic to those. Okay, if you use a harmonic one form, curl u is 0, so that has to be put in there. And so it's u harmonic to orthogonal to gradients. That's really harmonic orthogonal to gradients. That's divergence free with normal boundary conditions. So this says div u equals 0, u dot n equals 0 on the boundary. Thank you. Yeah. What's that?
Then u is curl.
Then u is what?
The range of curl.
Then u is in curl of H0 curl. So there's so many. The thing is, we have both this. We have so many different ways to write these spaces because we have that. The null space of 1 is the range of the preceding one plus the harmonic form. So we have between, R is equal to RD is equal to ND star perp, and that ND is equal to R of the previous D plus the harmonic forms. There's so many different ways you can write these things. So I got a little confused. But so the Poincare inequalities are certainly all right. And so we basically, so this Poincare inequality for one forms says that the L2 norm is bounded by the L2 norm of the curl for divergence-free things with appropriate boundary conditions. And the meaning of appropriate boundary conditions is different in these two cases. And there's a side condition of being orthogonal harmonic things, which is also different in these two cases. Okay? And there is no Poincare inequality at the end because it's just L2. And I think that's probably gotten everything. And so maybe it's good I got confused at the end to show that this is not, you have to be careful. But the main thing I want to point out is that there's a lot of information here, all these different kinds of mixed problems and so forth, all organized in this one thing. So if you just remember this sort of one framework, closed Hilbert complex, it has a Hodge decomposition, has a Poincare inequality, that sort of captures a lot of stuff. And what I'll do in the next lecture is I'll go back to the three forms of the abstract Hodge Laplacian, show their equivalent, and use the mixed form to show that it's well posed. And then where we're going with this, then we're ready to get to numerics. We'll discretize, and we will discretize in such a way that at the discrete level we get a Hilbert complex, and so this whole theory will apply, and that'll give us stability for the Hilbert complex, for the numerics. Okay, thanks.